All right. So this is lecture number 22. Today is the 2nd of December. All right. So then what is this whole idea of optimization? Well, we want to maximize certain quantities given certain scenarios. So let's see what that means. And a lot of this stuff, guys, is going to be a lot more word problems than before. So when we talk about like absolute max and min, we were given a function and we were given this interval and we figured out what's the highest point, what's the smallest point. And then we kind of ventured into the more word problem based kind of problems with absolute max and absolute min. And remember, even in these problems, in these examples that we've seen, they give us the function that we're trying to optimize. They give us the function that we're trying to find the maximum of or the minimum of. But now it's going to be our task to do so. So let me start with an example. So this is everything from now on will be on optimization, which is really the study of maximizing or minimizing a particular quantity. So example, let's start slow. It says find the dimensions of a rectangle with a perimeter of 100 feet that has the largest possible area. So these are the kind of problems that we're going to be doing a lot more of. So now the question is, where do we begin? Where do we begin? What is it? What is the Santiago? Yeah, you can draw it out. That's going to be actually one of the most important things we do. We're going to have to draw things out just to give us a better understanding. But what I just want to say, what is it that we're trying to optimize? We're trying to find the largest area. So our area is the quantity we want to optimize. So area is the quantity that we want to optimize. In this case, we want to maximize this. So we want to maximize the area, but there are certain conditions that restrict our rectangle, right? We can't just create a rectangle that has infinite side lengths. It's just something that's just never ending. There's a certain restriction, and the restriction is given by what it says that the perimeter has to be 100 feet. So that's another thing. Now you're gonna have to consider what are the restrictions. So this is my restriction or my condition. My condition is that the perimeter must be 100 feet. So far, this is what we have. And Santiago had a great point. Why don't we sketch the figure? So we all know what rectangles are. That's what we have. Now, all we know is that the perimeter, P, my perimeter, is 100 feet. But does anybody know how do you get the perimeter of a rectangle?
By adding all the sides up?
By adding all the sides up. But do we know the side lengths?
No.
So
But
then,
I was thinking, like, could you divide 100 by 4?
okay, if you divide 100 by 4, you get 25. And then what do you do with that?
Um, hmm.
What's
My
the idea?
area?
The idea is that I want to maximize my area, right? So you could be right. You could be right that the maximum area of this rectangle would have to be 25 by 25, which is 625. But then my question is, how are you so sure? Why wouldn't other numbers work? There are other numbers that when you add them up give you 100 as well. It doesn't have to be 25. So the thing is that we don't know yet, but we're on the right track, Santiago, because to find the perimeter, you have to add every side, right? But
Yeah.
then I'm telling you, we don't know the sides. So then if we don't know the sides, what should we do? Badur says 2L plus 2W. So what's L? What's W? That's right. We make, guys, this is the a very key part here. We're gonna have to create variables. We have to create our variables now. You see, we're not given anything. We're just given words. We have to create them. So let's create our variables. You can say L, W, X or Y, A, B, C. You can choose any number letters, right? But for now, I'm just gonna make it X and Y. So I'm gonna let X equal the width of rectangle, and I'm gonna let Y equal the length of rectangle. So then this will be X, this will be X, this would be Y, and the below would be Y. So then what would be the formula? It would be you add 2x with 2y. You guys see that? And now what's the restriction that I got? Or what's the condition? What's my restriction or condition? My condition is that Fujing, that's right. I'm gonna say that the perimeter was twice x plus twice y. This is 100, and we can do better. We can do a little bit better than this, right? 2x plus 2y equals 100. What if I divide both by 2? I can simplify this a little bit more, right? And I get x plus y is 50. This is my condition. I don't know what x and y are. I don't know yet. That's what I'm trying to figure out. But I know for a fact that if I were to find x and y, if I add them and I double it, I would get 100. Or in other words, if I add x and I add y, if I add the length of the rectangle with the width of the rectangle, it has to add up to 50 because of my condition. Now I'm trying to figure out of all of those rectangles, whose length and width add up to 50, which one of them has a maximum area? Which one has an area that's bigger than all the other ones? Like for example, I can for example put this as 1 and 49, that would work, or 2 and 48, so on and so forth, right? But which one of those, when I multiply them together, would represent the biggest area? So now I'll have to figure out what is the area what is the quantity that we want to maximize, or in this case optimize, quantity to be optimized. Well, we identify that in the beginning. I want to optimize or maximize area, but the area of what? I want to maximize the area of what? I want to maximize the area of a rectangle, right? Yeah, Fujing's already ahead of the game. Yes, that's right. So then, that's right, Fujing. So the area of a rectangle is the length times the width, x times y. Now the problem here is that we're not accustomed to having two variables to represent a quantity, right? We usually define a function in one single variable. So then my task is to rewrite. So I want to rewrite as a function of one variable, not two. I have two variables. I only want one variable. Now, how do I do that? Well, I use my restriction. So then use restriction. To solve for one variable in terms of another. You guys see that? I can take the restriction x plus y equals 50, and I'm going to say, hey, I'm going to solve for y. I'm going to get y by itself. And when I do that, what do I get? I get y equals 50 minus x. Now, why is this better now? Because now look what I can do. I can plug that y equals 50 minus x. I can plug in the 50 minus x into y. And now look what happens. I get that the area is equal to x multiplied by 50 minus x. And look what I just did. I rewrote my quantity area as a function of only x. And so then I can rewrite this as the area is a function of x. And I can represent this as 50x minus x squared. Do you guys see that? So the area function, this is my area function, is a parabola, given the way we have this structured. And now what is it that we want to do with this area function? We want to find the maximum. But haven't we done this already? Didn't we do this last time? So now I want to maximize. I want to find maximum, or I should say the absolute max of a of x. Because isn't that the whole point of this? I want to find what's the maximum area. So then what do you do after this now? What did we do in the previous examples last class? We always have to do what first? Anytime we want to find maximum. That's right, Fujing. Derivative. So what's a derivative? I got 50 minus 2x, and then what do I do? I set it equal to 0. And then what do I say? I solve for x, so then I get 50 equals 2x, which means that x is equal to 25. What is this called? This is my what? This is my critical number, right? This is my critical number, and this is a parabola. So either my critical number will be a maximum or a minimum. But we should already know that this will be a maximum. And just to make sure, we can apply the second derivative test. What's my second derivative? Second derivative is -2. It's always negative. So this is a constant, right? Constant. Which means always concave down. So if it's always concave down, that means that the maximum occurs, right? Maximum occurs at x equals 25. So I know for a fact that the area is the maximum when x equals 25. And so then, Santiago, you may think, oh, I didn't have to do all of this because all I had to do was divide 100 by 25. But it's not always that simple. But in this case, it is. In this case, it just so happens that it works out that the area that's maximum is a square whose side lengths are 25 each. So if x equals 25, and that produces a maximum for the area, what would be the y value? Well, we're going to use y. Remember, y was 50 minus x. But if I found x to be 25 already, right? If I found x to be 25 already, then when I plug this back in here, I get also 25. So then I get that y equals 25 as well. And then if we want to do one further, right? After we found the side dimensions, then what would be the area? The area would be x times y, isn't it? Which is 25 times 25, which is 625. And this would be 625, I think it's feet, right? Let me just, yeah, it's feet. So it's feet. So make sure you keep the units, feet. This is squared feet. So then we can sum this all up. Let's sum this all up. So what's the conclusion behind all of this? The conclusion is that a rectangle with perimeter of 100 feet has a maximum area of 625 feet squared if each side, if I should say, if both the length and width equals 25 feet. Okay? So that's the idea. The idea is to uh, find out what is the quantity that we want to maximize or minimize, find a restriction, represent that quantity that you want to maximize or minimize as a function of a single variable, and then once you have that function, find the maximum point using or minimum using first derivative or second derivative tests. And then you're able to figure out the rest of the problem, and you put it all together. So of course, this is the simpler kind. They can get quite complex because the hard part is to figure out the geometry. So a lot of this requires you to understand geometry um, a little more than other problems do. Okay. All right. Any questions about this? Does does it make sense what we're doing here?
Yeah, seems pretty clean.
Oh, it's clean, huh? Well, I'm
Yeah,
happy. Yeah, this is like to me I consider this like a story. Like you have to like really learn the beginning and end and the middle parts. So and each of these kind of problems has is a different kind of story. So you have to be able to be flexible and see how you have to alter your approach. So let's look at another one. Okay, so I'm not a great artist as you all know, but this will start out with a with a little drawing. So let's make believe this is a river, right? This is a whoa. Hold on. Okay, so we have this river here, right? And then we have some farmland. We have some farmland, and I'm gonna draw it like this. And this farmer wants to enclose a rectangular piece. Um, and let me just see. Yeah, and so he wants to enclose a rectangular piece of land next to the river. So there's not gonna be any fence on this side of the coast on this side of the riverbank, right? But you do have this kind of setup. So he has fencing all around the red outline, and we're gonna call this X, right? This is X, and this will be Y. Now, what we do know is that he has a total of this farmer, let's call this farmer um, Mr. Farmer. So the farmer has a total of 3,000 yards of fencing. So he's that has 3,000 yards of fencing, and he wants to create a rectangle that encloses a rectangular piece of land in this manner. Now the question is, he wants to, of course, maximize that area given this condition that he has. So the idea is, yeah. So the question is, what is the largest? What is the dimensions? Sorry, what are the dimensions? What are the dimensions of the largest? No, yeah. What are the dimensions of the rectangular field that represents the largest area? And the second thing is, what is the largest area? So this came with the drawing, so we don't have to really draw this since it's already there, right? So I got the drawing done, and then the next thing I had to do was what? Create variables. My variables are already given to me as well. X represents the width of the rectangle, Y represents the length. So now the question is, what is the restriction? How do I write my restriction or my condition? What is the restriction behind this problem?
The fencing is 3,000 yards.
Yes. So the fencing is 3,000 yards. So all of this here, that's my restriction or condition, right? So now the question is, how do I represent that mathematically? How do I describe that condition mathematically? 2x plus y is 3,000. You're almost right, Badur. You're missing something. I did not just draw this out of nowhere. This is also part of the the diagram. So it's not going to be 2x, it's going to be 3x. So I'm going to have 3x plus y. That equals 3,000. Do you see that? So he wants to design it in this way. He just doesn't know how big x should be. He doesn't know how long y should be. He doesn't know. But all he knows is that he wants to maximize the area that this fencing would enclose. You see, this stuff gets interesting. Okay, so that's my condition. And then what's the optimization? What is the optimized quantity? What do I want to optimize? I want to find the largest area. So then the area of what? I want to find the area of the whole thing. So what's this area? How do I represent this whole area? That's the area of a rectangle, which we just discussed last time, right? It's the same kind of similar setup here. It's going to be x times y. That's the area of a rectangle, x times y. Now, what's the issue here? Again, we have a quantity that is dependent upon two variables, x and y. We only want one. So then what do we have to do? Go back to our condition and solve one variable in terms of the other. So we'll look at our condition, 3x plus y equals 3,000. So which variable is it easier to solve for, x or y?
Y.
Obviously, it would be y. So then if I subtract 3x on both sides, what would my y value represent? It will be represented by 3,000 minus 3x. So my y value is 3,000 minus 3, whatever 3 times x would be. And then I can do what? Then I can sub this into the y value here, and then what would I get? I would get a function of the area is a function of x, which would equal x multiplied by 3,000 minus 3x. And then I can distribute, and I get 3,000 x minus 3x squared. Do you guys see this? It becomes very similar now, right? Do you see the structure behind this, the pattern? So this is the quantity that I want to optimize, or I should say I want to maximize. So how do I maximize this? What do I do to maximize this?
This is the first derivative.
First derivative. So my first derivative, what's my first derivative? I get 3,000 minus
Minus
6x.
Yeah.
And have to set it equal to 0. And have to solve. So then I get 3,000 equals 6x. So then divide by 6, divide by 6. And what do I get? I get that x equals what? 500. So that's what the x will be. And again, this is my critical number, right? This is my critical number. Now, I just want to make sure that this is what I want. So then what can I do? I can use the first derivative test or the second derivative test. Either or, but this seems to be a lot simpler if I use my second derivative test. So what's my second derivative test? I find the second derivative and consider the concavity. But this is one of those problems again that's always what? It's also always negative. If your second derivative is always negative, no matter what the x value would be, then it's always concave down. If I have a function who's concave down always, and there's one critical number, then that critical number must be the maximum. So a maximum occurs at x equals 500. So we know for a fact that the maximum of the area occurs when x equals 500. So once we have x equals 500, we get to figure out what's the dimension of the y. Remember what was the y? So find y now. Well, I know that y equals 3000 minus 3x. If I found out what x is, all I have to do is plug in. And I get 3000 minus 3 times 500. That equals 3000 minus 1500, which is 1500. And this is 1500 yards. So the dimensions of my fencing, right? The dimensions of my fence will have to be the following. It would have to be, this would have to be 500. This would have to be 1500 yards. In order for what to happen? In order to the area be maximum. Don't you guys think that's awesome? I don't know about you.
Pretty cool.
When I came across this, I'm like, wait, you can find exactly the dimensions that exactly create a maximum, and you're 100% sure of it, and there's no doubt about it. Like this is not ballparking it. This is not estimating. Oh, it might be this. It might be that. This is exactly true, 100%. Any other dimensions would not create the maximum. It would create an area, but it won't be the maximum. So then this becomes a very powerful, useful tool because maybe you're trying to maximize some other quantity, and if you can represent it mathematically, you can always find the maximum using calculus. So great. So we found that the width or the dimension of the width of the rectangle must be 500 yards and the length should be 1500 yards. So then what would be the maximum area? The maximum area is what?
X times Y.
Right. I already know what x is. It's 500. I already know what y is. It's 1500. So then what would be the area, the maximum area?
750,000.
Yeah. 750,000 what?
Uh, is it yards?
Well, we're talking about area.
Oh,
So
so square feet.
it's gonna be squared yards.
Oh, squared yards. Oh, okay.
Yeah.
Makes
So
sense.
square yards. And that's gonna be the maximum. You guys see that? Let me just see something. Okay. Make sense? Does this make sense, guys? Any questions about what we're doing? Is anyone completely lost? Is anybody having like, wait, what is this all? What is this all for? Okay, so if nobody has any questions, let's move on. Okay, so I'm gonna give you another problem here that
Oh,
it's kind of
Professor,
yeah.
sorry. Do we have to write the conclusion?
Oh, yeah, we can write yes.
Okay.
So put it all into one sentence. So we would say what? The maximum area enclosed by 3,000 yards of fencing would occur when x equals 500 and y equals 1,500 yards, producing 750,000 square yards of an enclosed area. That's right. We always want to sum up what we find at the end. It's a very good technique to have, be able to sum up things into one complete sentence. Okay. Now the next one that we're gonna do is a pretty classic one. It's a classic optimization problem that they always bring up. We always bring up as a an example. So let's see what this is. So we're gonna say by cutting away identical squares from each corner of a rectangular piece of cardboard and folding up the flaps and open box is made. If the cardboard if the cardboard is 15 meters long and 8 meters, sorry, not meters, inches. Meters will be way too big, be humongous. 15 inches and 8 inches. And 8 inches wide, find the dimensions of the box that will yield maximum volume. Again, this is classic. I'm gonna write this over here. Classic. This is a classic example of optimization. So the ones that we've done are the easier kind, or like the the more like introductory ones, right? So now that we have a better idea of what we're doing from the basic level, now we're going to kind of work our way up a bit more into the complexity of the problem. So now here, we have to kind of envision this. We have a cardboard that's rectangular again. So we like these rectangles. But what we're going to do is we're going to cut away the corner. We're going to cut away each corner. And those what we cut away are identical squares. So every corner we cut out the same amount and it's the same square. And whatever is left over, right, after we cut out those squares, we're going to fold up the flaps and create an open box. I don't know if you guys can envision that. And now the question is, if this cardboard rectangular piece is 15 by 8 inches wide, right? If 15 inches long and 8 inches wide, how much should I cut away so that when I create this open box, it creates a box with the maximum amount of volume? Do you see how this problem now is much more complex than the ones that we've done? But what's nice about it is that calculus solves this the same way. Doesn't it's going to be a different kind of problem in terms of um, the the quantity that we're optimizing here. In this case, we're not optimizing or we're not maximizing area, we're maximizing volume. But the idea is that we still will get a function that we can find the maximum of using calculus, using first derivative. Okay, so now that we have this kind of a little bit understood, let's first draw this out. So drawing always helps, guys. So draw a sketch. So what we're drawing a sketch of? Rectangles. And what do we know about the rectangle? We know this is 15 feet. Not 15 feet. What am I saying? 15 inches. And we know that this is 8 inches. Now, what is it that we don't know? What don't we know? What is it that we're going to do?
We don't know the
We're going to cut, right? We're going to cut away.
the
We're going to cut
four
away squares.
right.
And they're all identical. They're all the same. Do we know the length of these squares?
Well,
So then what do you think we're going to do? What's the variable we're going to say? If we don't know the lengths of those squares, why don't we call those lengths x? I don't know what they are. These are all x. Does this make sense? So then we're going to create our variables. We're going to say x is equal to the side length of identical squares cut from the corners. That's what x is. Now, let's cut them out. What happens if I cut it out? What happens if I cut it out?
it's gonna look weird.
Huh?
I think it's gonna look weird.
It is going to look weird. So let's see what happens.
Well, you won't have 8 inches then, right?
No, you won't. You have less.
Yeah.
You would have less. So then let's erase this. Do you see this? I don't have this anymore, right?
Right.
And then these are the flaps that they speak of. And we're gonna fold that up. But before we do that, right, you said we're gonna have less than 8 inches and we're gonna have less than 15 inches. So how much am I gonna have now instead of 8 inches?
Would you divide by 2?
What would this length be? If this whole length, think about this, if this whole thing here was 8 inches, and I took away x on one side and I took away x on the other side, then what would be this portion that's remaining? What would that, how would I
4?
represent that?
Would be 4?
No,
No.
I took away x twice.
Oh, X. Oh,
I took away x twice from 8. So this would be 8, 8 what? This would be 8 minus, who has it? That's right, Fujing. It would be 8 minus 2x. Do you see that? If the whole thing is 8 and I took away x, I took away x, then the remaining is 8 minus 2x.
oh,
And then the
okay.
same thing happens to this portion here. If this whole thing from here to here was 15 and I take away x from here and I take away x from here, I take away a total of 2x. So then this new length here would be what?
15 minus 2x.
Okay. Now we're gonna talk. Now we're talking. And now I want to create a box, right? I want to create an open box. An open box. So how is that gonna look like? So you have to. We're testing our artistic abilities here. And as you can tell, I'm not the artist at all. So then this is what I'm gonna have, something similar to this. Do you see this? Now the length here, right? This longer length here would be 15 minus 2x. The smaller dimension would be the width, which is 8 minus 2x. Now, what would be this little height here? What would that height be? This thing here. What would this be? What's the height of my box represented by? X. That's right, Badur. It's X. It's X. Because these are X's here. These are all X's. So if you open that flap, if you connect those flaps, that little height there is X. So guys, you see how much more work we had to do for this? It's not just, hey, what's the area of a rectangle that's the maximum? No, it's the area of a rectangle, of a volume of a rectangle, of a box that comes from cutting up the corners of a rectangle. So then we really have to dig deeper here. And so now this is what I want to maximize. I want to see, hey, how can I create a volume that's of maximum? But just think about the bigger picture. Think about how I think it's like magic. Cause so you're to tell me that if you give me a rectangular piece or cardboard, right? And if I were to cut up the corners, I can tell you precisely what you should cut out so that when you create this box, it's the maximum volume. Is that kind of useful information? Maybe if you have a company that sells rectangular boxes that you want to maximize your volume, given a certain amount of finite supplies. that would be very useful information for those kind of people that are into that things. But then there are other kind of scenarios that you also want to maximize. Do you see? So this is how powerful calculus is. It and just in general, this is how powerful mathematics is because the uh it gives us the information that we need in order to make the appropriate decisions that would benefit us. So it helps us. Make sense?
Yeah.
So I drew it. I created the variables. Now, now what do I do? So remember we usually we write our condition. Our condition is already described here. Our condition is that the rectangle has these dimensions 15 and 18, 15 and 8. That is our restriction already. So we already have our condition is already embedded in here. We don't have to like do anything else. It's embedded. Restriction is embedded. So this is my condition that the length equals 15 and the width equals 8. So then what is it that we want to maximize? What do we want, what volume do we want? What's the quantity that we want to maximize? It says I want to find the dimensions of the box that will yield the maximum. Whoa, what the? I want to find can't believe it just disappeared like that. I want to find the dimensions that maximize my volume. So I want to maximize my volume. How do you find the volume of a rectangular prism or of a rectangular box? Length times width times height. What's my length? What's my width? What's my height? Look what I got. I got a volume that I have 15 minus 2x as my length. My width is 8 minus 2x. And I multiply by x. Now, do you see how my volume is a lot more complicated here? It's not a parabola. It's not a quadratic. But that doesn't matter. I can still find the maximum using calculus. So then what I would do is I would expand it. So then 15 times 8 is what? 120. So you FOIL this 15 times 8 and you get negative 30x. You get minus 16x plus 4x squared. And I multiply this by x. And then I get 120x minus 46x squared plus 4x cubed. This is what I want, guys. I want my volume to be of a single variable, and I did it. And this is what I want to maximize. This is what I want to find. I want to find the maximum of this. So are we all on the same page? Do we see how we get to this point? Do you see the setup here?
Yeah.
Okay. So then now what is it that we want to do? If I want to maximize this, what's the next step? I must do what?
First the derivative.
First derivative again. You see, now this becomes second nature now. First derivative. So what is the first derivative? I get 120 minus what? 92 x squared oh no, sorry, x plus 12x squared. And I set it equal to 0. And then what?
You would
Then
have
I
to
have a quadratic, and then I must try to do what? I'm gonna see if I can solve this. So how do I solve this? And let me just rearrange this. 12x squared minus 92x plus 120 equals 0. Now, what factors can I factor this? I can factor out a 4. That goes into everything. So this goes 3x squared. 4 goes into 92 how many times? 23 times. So 23x. And then this goes into 4 30 times. Okay. And now can I factor this even further? Is this factorable? Anybody out there? So normally we would try to see, right? If you multiply 3 and 30, what do you get? 90? And see what two numbers multiply to 90 give you some kind of number for 23 when you add up to 23. Are there any factors of 90 that when you add them up give you negative 23? It looks like there isn't. Is there? 18 and 5. That's right. So then 18 and 5 is the correct two numbers that multiply to 90. But they have to be negative, right? So this is what I would write. This would be 3x squared minus 18x minus 5x plus 30. And that 4, we don't have to worry about that 4 anymore. We could just divide the 4 out, and we're left with this equals 0. And then we can combine, right? Factor by grouping, and we get what? 3x is x minus 6. So factor out the negative 5, and you get x minus 6 equals 0. And then this becomes x minus 6, 3x minus 5. And then I get x equals 6, and I get x equals 5/3. I get two critical numbers. Hmm. Now the question is, which one will produce the maximum? You can't have both of them. I mean, maybe you can, but most likely than not, right? You're not gonna have both being the right dimension. So how do we determine which one is the maximum, which one is the min? We can use what? The second derivative test. What's my second derivative? Well, I could just take the derivative of the first derivative. And I get negative 92 plus 24x. And then I'll plug in 6. And I get negative 92 plus 24 times 6. And what would I get? Don't I get a number that's positive? 24 times 6 minus 92? I get 52. What does that mean? It means that my second derivative is positive. So if my second derivative is positive, what does that mean about the concavity? It's concave up. So then if it's concave up and I'm a critical point, then what is it? It's a minimum. So obviously, if I were to put the other critical number in, I would get a negative. But just to make sure no funny business is going on, I get negative 92. The 3 goes into 24. 8 times 5 is 40. And negative 92 plus 40 is negative 52 instead. And this is negative. If this is a negative, that means that this is concave down. If it's concave down, this means that this is a maximum. A maximum occurs when x equals 5/3. So then what do we say? Reject, accept. And so then what's the question asked again? It says find the dimensions of the box that will yield the maximum volume. So what are going to be my dimensions? So what are the dimensions of box? The dimensions of box with maximum area. Pardon me, maximum volume. So if I draw it again really quick, can't draw this for life, for my life. Yeah, it's not working like this. Hold on. If I do it just freehand, I think it's a little better. So what do I know about this box again? This was x, this was 8 minus 2x, and this was 15 minus 2x, right? But I just found out that x was 5/3. So what are the dimensions going to be? This is 5/3. What is this going to be? 8 minus 2 times 5/3, which is the same thing as saying 8 minus 10/3, which is the same thing as saying 24 over 3 minus 10 over 3, which is 14 over 3. Or in other words, 3 goes into 14 4 times. So this would be 4/2 uh, of, I think these are inches, right? And this would be 15 minus 2 times 5/3, which is 15 minus 10 over 3, which is the same thing as saying 45 over 3 minus 10 over 3, which is 35 over 3. And this would be 33 goes to 32, 35, uh, how many times? 11 times? 2/3? So these would be my dimensions. So if I were to cut 5/3 of an inch, or 1 2/3 of an inch on each corner, and I would put the flaps up, I would create a box with the maximum volume. Any questions about this? Is this all understood? Okay, so my conclusion is that a rectangular box, so actually I should say by cutting squares of side lengths 5/3 of an inch, the resulting open box has maximum volume with dimensions. The length would be 11/2 of an inch. The width would be 4/2 of an inch, and the height would be 5/3 of an inch. So
So
please,
that's
yeah,
it. The length and widths that we got represent the the lengths and widths with the cutted squares.
yeah. So after I cut 5/3 of an inch, squares whose side lengths are 5/3 of an inch from every corner, right? And I create this new box. This box that I will create that has these dimensions would be the box that has the maximum volume. If I were to cut the squares any other length, right? If I were to make it 1 inch, for example, if I were to make it instead um, 3 inches, if that were to happen, the resulting box would not be maximum volume. It would still have a volume. It just won't be the maximum. So under these conditions, if I were to cut squares and those squares all have the same size of 5/3 of an inch, the volume of this new box would be the maximum volume.
Oh, okay. So so the height is 5/3 inches, right? And that also
Right, because
each
Mhm.
square, each little square.
Yeah, because the height of this box comes from the fact that we cut away, we snip away, right?
Oh yeah,
So
right. Yeah, if you
yeah,
pick.
we snip away this X amount, right? We snip away this X, and then when you fold the flaps, right? You create this box, and this box here, this height, is exactly what X is. It's just by the way we constructed this box. We constructed it by a rectangular cardboard, and we cut away the corners, and we opened the flaps up and connected them to create this box. So the question was, what are the dimensions of this box so that the volume is the maximum volume? And it would have to be exactly what we found out. It would have to be these dimensions. It would have to be because first derivative, second derivative test, so on and so forth.
Oh, one
Okay?
more thing.
Yeah.
So would we have to provide the answer in a mixed number form, or could we do a decimal?
So the thing is, the decimal, I the thing is, this is an irrational. No, it's not. It's a the decimal is a repeating decimal.
Oh,
So it would be 1.66666666 repeating. And this will be 4.6666 repeating, 11.666 repeating. So it would be a little better for this context of the problem to represent it as a mixed number. Because this is the way we speak sometimes, right? 4 2/3 of an inch. Like just about these kind of measurements, we kind of speak this way. We don't say, hey, this is a 1 and 0.6666 inches. Even though we could say 1.6 inches, but that would be a approximation, right? The exact value would be 1 and 1.66666 repeating inches.
oh, I get it. Yeah, it
So,
sounds
so instead of writing that way, just this is just a convention, right? We would say, oh, this is 1 and 2/3 of an inch. So they're like, oh, okay, I got it, right? So now I would write this as 1 and 2/3 of an inch. But you would still be correct if you represent it as a decimal. It would still be right. It's just that it's more conventional to express it as a mixed number, especially when we talk about like measurements of this sort, right? They're not that big, they're kind of small. But the idea is that can we get to actually express the dimensions? That's really the idea. And 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 I want you to see how we go from the word problem, right? And how we're able to create this story. This is a little story that we have, you see? We have a cardboard box, and then we have a cardboard rectangle, and then we made it into a box. And then what do we want to do? Maximize this volume. How do I do that? We'll represent every side in terms of x. And once we have this, we're smooth sailing because then we can apply the first derivative, which we should be able to do, solve it equal to 0, find the critical numbers. Then we have to test the critical numbers. You can use the first derivative test or the second derivative test. It's just that the second derivative test tends to be a bit quicker for this purpose because all we have to do is plug in into the second derivative. And then when we do that, we figure out, hey, look, 5/3, when x equals 5/3, I have a maximum because my second derivative is negative, indicating that it's concave down. And the other value, it's concave up, so that would be a minimum. But we're interested in maximums. So we disregard the minimum, and then we find the rest of the dimensions. Does that make sense?
yeah, it makes sense. It's just that for this problem, for me
Yeah.
personally, I think it was finding like solving for zero was kind of difficult because we had to factor multiple.
Yeah. Yeah. But it's doable.
Yeah,
It's doable.
but it's
And let's say you weren't able to factor it. Let's just say you were not able to factor it. You can always, since this is a quadratic, you can always use the quadratic formula.
oh yeah, I forgot. You're right.
So the quadratic formula would give you the same solutions. It's just that we would always prefer to see if it's possible to factor because it's simpler. You see, it's just I get the answer simpler. I don't have to worry about the square root, squaring things, multiplying things. These numbers would be kind of big, I think. If we were to plug it in,
We're pretty
A,
big.
B, and C, it would be really big. But still, the result will be exactly 6 and 5/3. So don't worry about if you weren't able to factor it, but the idea is that you can always solve for it. You can always solve this equation.
Yeah. Other than that, the steps were pretty clear.
Pretty clear. Okay, I'm glad. I'm glad. All right, so we've been doing a lot of maximization. We've been maximizing things all around. So what if we have a problem that requires us to find the minimum? So we always want to maximize profit. We want to maximize space, right? We want to maximize, I want to maximize the area we've seen. I want to maximize the volume. But on another hand, we also want to minimize things. And one thing we want to minimize are costs. Okay. So it says, let's do this one. So we have a pencil cup, okay? we have a pencil cup with a capacity of 36 cubic inches. So a pencil cup is to be constructed with the capacity of 36 cubic inches is to be constructed in the shape of a rectangular box. Uh, rectangular box with a square base and an open top. The material for the sides of the box is 15 cents per square inch. And the material for the base, we're going to say, costs 40 cents per square inch. What are the dimensions of this box that would minimize the cost? So make believe you were in this position and you were selling pencil cups, pencil holders, and they were rectangular boxes, open top and a square base. And you had to pay out of your pocket to try to create these things. And you know that the material has this kind of cost, right? 15 cents per square inch for one side, and you have 40 cents per square inch for the base. You still want your cup to have a capacity of 36 cubic inches for the volume. You still want your box that contain this amount of volume, but you want to minimize the cost as much as possible. So then you have to try to figure out, wait, what would the dimensions be then? You would be interested in that. So you can minimize the cost. So now the question is, how do I do this? First thing we do is draw a sketch. What are we drawing a sketch of again? Well, we have a square base first. So my base is square. And I have some box here, open top. Not the greatest box in the world. Has something like this, right? And what do we know? What do we know? We have a square base, right? Do we know what the size of the square is?
No.
We don't. So then what do you think we're gonna say?
Substitute it for a variable.
Yeah.
So for
What
x,
kind of variable should we make every side of the square base equal to?
I would say x.
X. X works. x. So then I want to create my variable. So x will be the side length of square base. So that's the side length of my square base. But those are not the only dimensions of this box, right? We have x for the bottom, x for the size of the square base. Then what would this be here? What would this be? This is known as what?
Oh, the height.
The height. Do we know what the height is?
No.
No. So then what are we going to say? How do we represent the height?
H.
H. Makes sense, doesn't it?
Yeah.
H is the height. Height is the height of the rectangular box. Good. So we got X, we got X, we got H. What else do we know?
We know the volume.
We know the volume. This is going to be our condition. What's my condition, my restriction? My condition is that the volume. And what's the volume of a rectangular prism again? Length times width times height. But we know that the length and the width are the same. So we know that x squared times the height must equal what? 36. That's my restriction. This. X squared times height equals 36 cubic inches. That doesn't change. That's fixed. And then what's the quantity that we want to maximize or minimize in this case? What's the quantity? So this is when it gets a little more complicated. What's the quantity that we want to minimize?
We want to minimize the cost.
The cost. Now the question is, what
Which
is, how do
cost?
we express that? You see? You see how these problems get a little like, as you go along this kind of optimization world, they get a little more complex. At first, it was like, oh, it's just the area of a rectangle. Oh, it's fine. Easy, this, that, and right. It's like, oh, easy going. And then we started talking about creating rectangular boxes out of nowhere. And now we have this rectangular box, and we're given the volume. But we want to minimize not the volume. The volume is stationary, it stays the same. We want to minimize the cost. So the question is, how do we represent cost as a function? Anybody have any ideas?
I mean, cost function exists.
Yeah, but this is not the same cost function
Right. Yeah.
as you may think about like selling units. That's not. We're talking about cost of producing material.
So we
There's a
have.
material for the sides.
Yeah. So there's two 15 cents per inch squared for each of the sides, and the base is 40 cents.
Yes.
Just don't know which one to use.
No, we have to use both because we have the sides. The sides are this. I got this is my sides. I have four sides. I have an open box, right? And I have a square base. The base is the 40 inch. The
Oh
base
yeah.
has material that costs 40 cents per square inch, and the sides have material that costs 15 cents per square inch. But my question is, how do I represent this function? That's the hard part. This here drawing is fine. Creating the variables is fine. Even finding this condition is fine. But finding this quantity actually is not that straightforward if you don't know how to begin. So let me start with this question. what would be the cost of producing material for a square base where each side is x? What would be the cost of the square base?
Um, could it be x squared plus 40 cents?
Close. It's not x squared plus 40 cents.
Or is it 40 cents squared?
It's 40 times x
Okay.
squared. Do you guys understand that? That's right, Badur. It's x squared represents the area of the square base. So given the area, we know that for every square inch, it's 40 cents. So this would be 40x squared. If you understand this, then you understand the rest. Then what's the cost? This is the first thing we do. The second thing is what's the cost of sides? What's the cost of the sides?
15x squared.
So it's 15. Okay, be careful though. What's the area of one rectangle here? It's not x squared.
It's x
It's x times what?
times height
Times height. So that's 15 times what? X
times x
H.
h. Wow.
I
Okay.
know. And then that's only one of them. That's only one of the sides. How many other sides do you have that are exactly the same?
One more.
You have four.
Oh, yeah, four sides.
This is only for one. 15xh is only for one, but I have four. So I have to have multiply this by what? Multiply that by four. And what do I get? 60xh. Do you see that? So then what would be the cost function? The cost would be, the total cost is what? 40x squared plus 60xh. That is the total cost. That's it. What's the issue though? The quantity that I want to minimize, what's the problem? It has an x and an h in it. I only want my my function my quantity to be expressed as a function of one single variable, only of one. So then what do I have to do? I have to use my condition. And I have to see how can I solve for one of the variables. So for which variable is it easier to solve? Is it for x or for h?
For h,
H. So then what do I say? I say that h is equal to what? 36 over x squared. So wherever I see h, I replace it with 36 over x squared. So now my cost function c of x will be 40x squared plus 60x multiplied by 36 over x squared. Do you see? And then what cancels out? The x's, and then look what I get. C of x is equal to 40x squared plus, and I get 60 times 36. I get 21, 60 over x. This is my function. I did it. Do you see that? That's the function I want to minimize. Now this function is completely as expressed as a function of one single variable, x. This is not, this is the hardest part of this problem, I would say, is coming up with this equation. Because you have to account for many things. You have to account for the cost of the square base. Understand that. Cost of the sides. Understand that. Add them together. That would be the total cost in a material that you have to provide. So now what's the next step after we specify our function as a single variable? We have to do what?
We could use the first derivative.
First derivative. Our first derivative, c prime of x. Well, remember that it will be useful just to rewrite this as a -1 power. So this would be what? This would be, the derivative would be 80x minus 2160 over x squared. And we want to set it equal to 0. And I want to solve. So can I solve this? How do I go about solving this?
Move one of them to the other side.
Move one of them to the other side. Yeah, we could do that. So this becomes 80x equals 2160 over x squared. And then what?
Could you cancel the x or no?
No, we can't cancel the x. We're going to actually cross multiply. And I get 80x cubed equals 216, 2160. And then I can divide this by 80, divide this by 80, and I get x cubed equals 216 over 8, because the zeros here can cancel. The zeros go away. And so then I got x cubed equals 216 over 8. But what can I do now? I can take the cube root. And does anybody know the cube root of 216? Does that have a cube root? What's the cube root of 216? That's right, 6. So I get 6, and what's the cube root of 8? The cube root of 8 is 2. And 6 divided by 2 is 3. So I get one critical number, x equals 3. And now I want to see whether or not this is exactly the minimum that I want. So then I have to use the second derivative test just to make sure. And what's the second derivative? 80 minus, this becomes what? It becomes positive. This becomes positive 4320 over x cubed. And now you start to see it doesn't matter what I plug in for x. I mean, any positive number for x. If I plug in 3 here, I would get something that's positive. Because 80 is positive, and this would be positive. So two positive numbers add up to something positive, which would indicate that the concave up, which would indicate that there is a minimum at x equals 3. So then what did we just figure out? We figured out that the cost is minimized when the square base has a side length of 3. And now that I figured that out, I can figure out what h is. What would h be? Remember, h was defined to be 36 over x squared. But I found x to be 3. So I could do 36 divided by 3 squared, which is 36 over 9, which is 4. So the height of my square box is 4. So what would be my conclusion? To minimize the cost of the rectangular box, the dimensions of the square base should be 3" by 3" and the height must be 4" high, long, yeah, tall. So are we understanding the process here? Do we see how we get to the minimization of the cost?
Yeah.
What do you guys think about these problems? Is it hard, easy?
They're hard because you gotta like really picture it. Like you gotta remember that um the the rectangle, the 3D figure,
Yeah.
it has four sides.
Yeah.
Like I completely forgot about that.
Yeah, you have to account for everything. You have to account for everything.
Yeah, like you can't miss anything.
Nope, definitely not.
So like the picturing aspect of it makes it a little difficult, but if you nail that down, it should be pretty easy.
Yeah, so the geometry behind this, right? It's what you need a strong foundation in the geometry.
Yeah,
See, that's interesting. It's interesting how when you start learning mathematics, it's very compartmentalized, right? Like everything is like, okay, this is algebra 1, that's all only algebra, and this is only geometry, and then you kind of fit things in boxes, right? But you start to realize as you start to do more advanced things kind of just coalesce. They kind of intertwine with one another. So you need to have algebra down pat because it's embedded in geometry. And you have to know geometry because it's embedded in the world that we live in, right? We consider space, length, volume. We consider these things. And then if we have that understanding down pat, then we can understand how calculus, how derivatives even play a part into this. We're dealing with geometric shapes here. You see that?
yeah. So in the sketch right here, x is 3, the other x is 3, and the height
Yeah.
is 4.
Yes. According to what we just found, if we were to make a box like this, uh, the volume would still be 36 cubic inches, and the material that we would spend on making this box would be minimal. Any other dimension, if we were to create it so that the volume is still 36 square inches, any other dimension, I would actually have to pay a bit more. Can you believe that?
Yeah,
So
pretty
all
cool.
these things are important. The dimensions of the packaging of things are important because if you're somebody that is at the head of a company and you're trying to minimize the cost, right? You want to be able to optimize these things. And there's a mathematical someone, and then you would ask somebody, hey, can you guys figure out what's the dimensions of this box so that I can minimize the cost? And then somebody would be like, yes, of course. Let's do some calculus. And boom. And nowadays people don't even use calculus because most of this stuff is most likely already programmed in a lot of software packages, right?
Oh, yeah, never mind. I was gonna say you could pay that person more for what he knows, but computers could do that.
Yeah, a lot of computers could do that, but the thing is, you have to be careful with that. See, I know some other student brought this up, like, oh, what's the point of learning all of this if we can just Google stuff, right? But you have to be careful with that because are you just gonna rely on some other software? Well, what if
Anything could happen.
yeah, what if like just Google just goes bankrupt or I don't know, even though that's like super like far-fetched. But I'm saying like what if we live in a post-apocalyptic world where like there's no internet, there's no Google.
Ooh, so then we go back to our fundamentals.
The point is we have to it's more useful if we understand how things work from behind the scenes.
Yeah, like you
How to,
said previously, like this is like calculus and the application, like it helps us problem solve, right? That's the
and
skill.
you can take that any time of the any time of day. You can take that any position in the any location in the world. You can take that in any time period of history. You have to know how to solve problems.
And that's
And
yeah,
mathematics is just one arena in which the problem solving is a heavy component of it. It's a big aspect of mathematics. It's not the only place, right? You can do that in chess too. You can do that in other another fields where you're required to try to figure out a final answer, right? But mathematics is very good because it's so broad that there's so many different kinds of problems that it helps with your problem solving ability. It does.
yeah,
So it's like a training. It's a training of the mind at the very least. At the very least.
yeah, and it's kind of satisfying seeing how
And
things
and
work,
that's when it gets fun because
right?
you get satisfaction out of solving something. So that's really what it is. When we think, oh, when we solve a problem, it's like a human desire has been fulfilled in a way.
Yeah, it's a plus plus. You get the knowledge and you have fun.
Yeah. That's what I hope everybody has that kind of experience.
Yeah, but it's complex.
It is. So
That
let's see if we can do another one of these. More more maximization. So let's say if I want to design, right? It's called a Norman window. A Norman window is a window. You've probably seen this before. It's a rectangular window, and then it has a semicircle on top, right? You've seen these kind of windows. And so this is a semicircle. This is a rectangle. This is a Norman window. And I want the perimeter of this window, perimeter of window to equal 28 feet. That's what I want the perimeter to be. So it says what is the maximum? What is the dimensions of the window so that the it so that it maximizes maximizes the amount of light that goes through it. Sorry, what are, not what is. What are the dimensions? So we have the sketch of this, right? And I'm going to give you a few more dimensions here. So this will be the center of the semicircle. And I'm going to call this x. And I'm going to call this here y. So I created for you the variables. And I want to figure out a way that the perimeter is 28 feet long. That's the perimeter. So the perimeter would be all of this. That would be my perimeter. And I want the total perimeter to be 28 feet. It's actually no, the perimeter is all of this. Is all of this rectangle plus this. That would be the perimeter. And I want all of that to equal 28 feet, while at the same time maximizing the amount of light that goes through, which is equivalent to say I want to maximize the area. That's all I'm trying to do. Maximize area. So the first thing is, how do I represent the perimeter? How do I represent my condition? How do I represent my perimeter, guys? Well, how do I represent the perimeter of this part here? So, so how do I represent this perimeter here? Just this portion here. What would be that perimeter?
X plus Y.
I got y here. I got y here, right? Because it's a rectangle.
Yeah,
And this here would be what? It would be
X
2x.
2x.
Yeah, because this represents the midpoint of, this is the center of my circle. So this is the midpoint of the diameter, which is meaning that this is the radius of my semicircle. So if this is x, then this would be twice that. So this would be 2x.
So 2x plus y equals 28, or is it
So,
just
so it's a lot more though. It would be x, I mean, this would be y plus y. It's 2y, right? You'd have 2y.
right? Right.
And then you'd have plus 4x because you got 2x and 2x. But then you also have to account for this here. What is this? It's circular. So what would be, how do you find the perimeter of a circle? What is that known as? What's the perimeter of a circle? Also known as the circumference, guys. The circumference. What is the circumference?
2 pi r.
2 pi r. But that's the circumference of a full circle.
Oh,
What's
right.
the circumference of a semicircle? It's not 2 pi r. It's going to be pi r. It's half, correct? That's right, Badur. And then what's the radius? In this case, my radius is x. So this is actually pi x. And that would be the perimeter. It would be 2y plus 4x plus pi x. This equals 28. And if you want this to, if you want to combine like terms, you would write this as 2y plus 4 plus pi parentheses x equals 28. So boom, we got the condition. Okay, that's important. Now I want to maximize. So what's the quantity I want to maximize? Quantity to maximize. Well, what's the area I want to maximize, right? I want to maximize the area. So the area would be what? XY. That's the area of the rectangle. And I have to find the area of the semicircle. What's the area of a semicircle? What's the area of a semicircle, guys? What's the area of a circle?
Is it the radius?
The area of a circle is pi r squared.
Right.
But I want to find the area of a semicircle. So the area of a semicircle is half pi r squared. But my radius is not r, my radius is x. So I'm going to replace that. Pi x squared. And this represents the area of semicircle. Okay? Now, what is it that I want to maximize again? I want to maximize my area. The problem is I have a function of an area that it's expressed with x and y, but I only want one variable. So then what am I going to do here? What do I need to do? I need to get one of the variables expressed in terms of the other variable. In this case, I'm going to again solve for y, get y by itself. So if I want to get y by itself, I have to subtract the 4 plus pi x on both sides. And I get what? I get 2y is equal to 28 minus 4 plus pi x, and I want to divide this by 2. So I get that y is equal to 28. I could divide this by 2 minus 4 plus pi. I'm going to divide this by 2 x. So y is equal to 14 minus 4 plus pi over 2 x. The answer to this problem will not be so clean. It will be like a decimal because of the pi. So now I can replace this y with this expression. So this will be x multiplied by 14 plus 4 plus pi. Should be minus 4 plus pi over 2 x plus pi over 2x squared. And then I can distribute and I get, this is a function of x. This is 14x minus 4 plus pi over 2x squared plus pi over 2x squared. And I'm just going to do some more algebra, okay? I'm just going to do some more algebra. I get 14x minus, if I distribute this, I don't know if you guys see this. If I distribute, I can write this as parentheses 2 plus pi over 2 x squared. Do you guys see that? I can rewrite this as 4 plus pi over 2 like this. plus pi over 2x squared. Now, why do I do this? Because look what happens. I get 14x minus, this becomes minus 2x squared minus pi over 2 x squared plus pi over 2 x squared. Now that's interesting because the pi's cancel out. Just make sure that that's what happens. The pi's cancel out here. So I get that the area is really just 14x minus 2x squared. So it's actually not that bad at all. So my area is 14x minus 2x squared. And now I want to find the maximum. So first derivative, I get a prime of x equals 14 minus 4x. This has to equal 0. Then 14 must equal 4x, which must mean that x equals 14 over 4, which means that this would be 7 over 2, which is 3.5. 3.5 what? This is feet. And just to make sure this is a maximum, which it would be, I do second derivative. Second derivative test gives me -4. This is always negative. So that means that this is always concave down. If it's concave down, then it must mean that x is a, it must mean that when x equals 3.5,
The maximum.
there is a maximum, right? Maximum occurs. That's kind of cool though, that the area here cancels out. It cancels out with the pi's cancel out. That's very convenient. Very convenient. Mm-hmm. And so then the maximum occurs, and then that would be it. And then we would say, what are the dimensions? What are my dimensions? So then the dimensions of my Norman window.
Professor, I have a question. You
Yeah,
have to solve for y?
yeah. That's what we're trying to figure out. We're trying to figure out the dimensions, right? Because again, my Norman window is what is given by a rectangle, and it has a semicircle like this. So if I figured out that this has to be 3.5, then that means that this width of my window must be what? 7 feet? And then what would y have to be? Well, what was y? Y was what? We found y to be 14 minus 4 plus pi over 2x. But x here is 3.5. So this is where the decimal will come out. This is 14 minus 4 plus pi over 2 multiplied by, I'm going to leave it as a fraction, 7 halves. So this will be y is equal to 14 minus, then I can distribute and I get 28 plus 7 pi over 4. And then if I write this out, this is 14 minus, I can write this as 28 over 4. And just make sure you put the parentheses. This is 7 pi over 4. 28 over 4, I can reduce that to 14 minus 7, right? 7 plus 7 pi over 4. Then I can subtract and I get 14 minus 7 minus 7 pi over 4. And I get this is 7 minus 7 pi over 4. But of course, we're not going to say, hey, this is 7 minus 7 pi over 4 feet long. We're going to probably use a decimal expansion here. So I would say this is 7 minus 7, let me put this, 7 pi over 4. And I get 1.509. Now that's a little strange. 7 minus. That's a little strange because it looks like the y value is smaller than the x value, which I don't think that's supposed to happen. So let me just see something here. We got that 28. Yeah, so I think it's because we included this part. We included this portion here as the perimeter as well. So that's why it's going to be a little smaller. So we got this to be 1.5. What was it? 1.5. Yeah, around approximately 1.5 feet. And and that would be the dimensions of my window. That's what produce um, the maximum area, given the fact that we only have 28 feet of the perimeter here. Does that make sense, guys? Anybody? Ali, Arnab, Badur, Demetrios, Derek, Coco, Laura, Lucy, Max, Menachem, Pedro, all of you out there, Ryu, Vitali, is everything
Yeah, it makes sense. I'm just like processing everything.
processing
Yeah,
everything?
same here. I'm just looking at how you got the square, the rectangle, and then I'm processing how you're adding the half circle into it.
Okay, so it's a lot to process, huh? A lot of geometry.
The last time I saw this was back in 2014, so like it's a lot.
I see. I see. So yeah, so for this guy, um for this whole topic on optimization, the geometry that you have kind of just forgot about, you got to bring it back because most of these problems will require you to know the cube, rectangular prisms. Um,
Professor, just a quick
yeah,
question. Does it get any harder than this?
no.
Okay. So all right. So because I'm looking at it and it's not that bad. Like compared to like most of our thing, like if it's on a test, this is the first thing that I would go for, you know? Like on the
Okay.
final, this is probably the first thing that I would like aim for. Maybe the simple like, derivatives. Can you also give would you know if there's like what's gonna be on the final and stuff like that? Because that's like my main concern.
Yeah, so the final is coming up, right? Um, so the idea is that it's gonna be primarily based upon everything that we're doing now, right? Optimization, absolute value, but it's also gonna be cumulative. That's what finals usually are. They're cumulative. So it's everything that we've covered, including all of this stuff. So everything that we covered in exam number 1 and number 2 will be revisited again on the final, which could be either good or a bad thing. I would say it's a good thing because you've seen it already. You see what I'm saying? So all you have to do is review the things that maybe you're not so comfortable with and review those things like implicit differentiation, for example, related rates. Those things will be appear again.
Professor, is there more time?
It's 2 hours.
Oh, 2 hours.
You only
Yeah.
get three.
But like, I imagine that there's gonna be like
It's
one
it's
question.
exactly what you guys have been receiving. 2 hours, just like a full
Oh,
length 2 hour exam.
Can we get practice exams if that's possible?
Well, the thing is, that's what I do. I give you review. I give you review. I give you more than a practice exam. A practice exam would be like this. Would be I'll give you what, like 6, 7 problems on the exam, right? A practice
Yeah.
exam would be something of the same kind, right? 6 problems. I give you 6 problems for one of those questions. So in a sense, the review sheet encompasses 3 or 4 practice exams in or 5 practice exams in one. Do you understand?
Yeah, I get it. So when are we gonna get the review sheet again? Like, because I just want to like just want to aim as high as I can. Like, like I just want to like just go through the problems, like understand it. Like it's been stressful, man. It's like Queen's College stress and then classes stress, and then it's just life.
Life stress. Let me just tell you, we're all going through it. We all are.
And I feel like as soon as you graduate like from college, like I feel like there's barely any minimum stress, because like you like if you do what you like to do like as a career, I feel like it's just you waking up and then going to work and then like catering to your social life.
being
It's
happy.
like
I don't think it's that simple. I wish it were.
it's like like smooth sailing.
I would say, okay, listen to this. When you graduate from college, right? Do you know what they call the ceremony?
Graduation.
No,
Well,
Debt.
no. They call it commencement.
okay.
Do you know what commence? Do you know what commence means?
Yeah,
What
to
and what?
start. You're just starting.
It's the beginning. So you think, oh man, I made it through college. Oh my God, I made it. Oh my God. And that's it? And that's the hardest part of your life? No.
No, I mean like obviously there's grad school, but like I'm going to grad school for like economics,
No, don't even talk
so
about
that's like
grad school
two
is
years.
ridiculous. You think this is hard? Grad school makes this look like a cakewalk. I'm not even trying to I've been through grad school. I got a master's. It made my undergraduate experience. I'm like, what was I doing in undergrad? Because grad school is another animal. But that's not even the hardest thing to do. Grad school is
What's
not the hardest thing.
what's the hardest thing to do?
And just have you ever, wait, I think this is from a movie somewhere, but I think this is from Rocky, one of the Rocky movies, when he's older and he talks to his son, and he's saying nothing hits harder than life. You know Mike Tyson? You know about Mike Tyson?
There's a beast.
Yeah.
Yeah, he's an animal, right? And this guy recently, he's been in a lot of interviews. He
Yeah.
himself says life has been beating me up. And that's why you see a different version of Mike Tyson now. Mike Tyson is much more subdued, humble, right? He's still an animal, but he's different mindset because of
Right.
life.
Because he keeps fighting back. He's how do you say, resilient.
Yeah. But his career went from a
I mean,
height
I mean,
to,
I mean, you need to take into a factor what like a person's already been through and stuff like that. So like, let's say like if a person A's been through, like utter shit, like and like he has a taste of what the event B is going to be like like later on in life. Like I feel like I have older friends, so like I could like I could see a little bit better into the future, I guess, like the
yeah.
perception. And to me it's like that's a cakewalk. Like I rather be doing that because like I have more control over that. For this I feel like I don't have any like not to dive into like personal things, but like I wasn't supposed to like work. The only reason I picked up work is because like Queen's College, instead of like giving me my loans, they were just like, yo, you're stuck with 11.2K. You can't sign up for classes. Good luck. Like that's literally how I feel. Like so like
Yeah.
it's just like it really fucked me over. Like excuse my language.
Yes, you're being recorded, but don't worry. Yes.
But yeah, it's just like it's just like tiring, you know?
The thing is, that's life. You understand? That what you're experiencing is life. So there's circumstances in life where you have your hands tied, and what you have to do is figure a way out. There's no
Yeah.
way like you think, oh, that lifestyle, that's a cakewalk. Yeah, but that's their lifestyle. That's not you. You never know what happens after you graduate. You might think that, oh yeah, I got my dream job, and then you start to realize, oh, your dream job is not really your dream job, or what
Yeah,
you
you're right.
think, or what you think is what you want, right? And when you get it, it's not what you wanted, and you're like, oh snap, what am I gonna do now? From here on out, nothing gets easier. Let me just say that. I'm just gonna keep it short and simple. Nothing gets easier. Nothing gets easier, but that doesn't mean we gotta give up. Actually, the challenge is what's important. That's the whole point. You're supposed to welcome challenge. You'd be like, yo, bring it. Let me see what I can do with this. That's how you grow. It's through challenge.
Nah, nah, I'm about to give up.
No,
I agree.
no. See, that's the thing. You can't. Because look, let me just tell you something. You lose when you give up. You don't lose when you fail. That's what people have a trouble. That's what people scared of. They're scared of failing. They're like, oh man, if I fail, this, that, and third. That means if you fail, that means that you tried. If you fail and you have a heart and you have lungs that work and you have a brain that works, you're good because you can try again. That's the beauty in life. You can try again as long as you have it in you. But when you stop something, when you quit, that's when you lose. I'm just telling you from my experience. Because I know what that feeling is like. I know what that feeling is like of being at that point where you want to give up. Everyone gets there. No one is exempt from that. Every time you wake up, you're like, damn, I don't want to get up from bed. I want to stay in bed. Everyone feels that. But the people who overcome that feeling, they're the ones that are successful. They're the ones that keep going. So that what you experience, of course, your experience is specific to you, right? But the overall thing is that everyone experiences challenges. Just have to overcome, outlast it, and you'll see where you go. That's the beauty. You never know. This will be just a moment in your time. Oh, Queens College, it's just a moment in your time. You have so much more to go, so don't give up. And that's my 2 cents. All right, guys. Well, that was good. It was
Not
good
just a math
talking to you guys.
professor, but a motivational speaker. I love it.
Nah, it's just life.
I love it. No, it's true.
No,
Everything you
the
said is true.
motivation. Let me just tell you, motivation that comes and goes.
Right.
You need inspiration. You need
Mm.
something that wakes you up. That
The
that you would
consistency.
do this without someone paying you. That's the beauty. If you can find something to do that you don't mind doing it for work for dollars or for anything, like if you can do this just because you do want to do it, if you're able to do that for your
Right.
career, you won.
Right.
Like it will be terrible. It will be a torture if you do something every day and you get
That you
paid for
hate.
it, but you hate
Right.
doing it. Like that's
Right.
like to me, that's
Makes you
almost
sick.
like that's almost like a prison because you're
Right.
doing something every day you don't feel like doing. Why don't you find something that you would love to do, enjoy it, and whatever comes because you love it. And when you love something, it don't matter what comes. It doesn't matter. You're gonna find a way.
I agree, Professor. Thank you. And I love the background, by the way. It kind of, I was shook the first day. Now I'm like, I see.
So you like the blue?
Not, no, I'm saying the background of your
Oh,
profile.
my
Yeah,
background of my virtual
yeah. I'm
background.
like, are you in South Africa right now? Like a lion
Nah,
about
nah,
to jump
nah.
out or something? Yeah, I like it.
Now this is a picture I took. I was somewhere in the Mohonk Preserve, somewhere upstate, hiking.
Oh,
I
okay,
took that picture. So yeah, that's all it is.
it's cool.
All right, guys. Well,
Thank
this
you
was a
so much.
great time. I'm glad we got some, some stuff out of our chest.
Thank
Hopefully
you
have
so much, Professor.
some more interesting insights as to what life is all about.
Yes, sir. Thank you so much, Professor. Have a good day.
All right, and see you all next week.
Professor, quickly, when are you posting the review sheet?
Oh yeah.
Oh, the review sheet, I would post it. So our final is a December, I believe. What is it? The 15th, I believe. So I would post it next week.
Yeah.
And we have a
I,
quiz next Monday and next Wednesday.
I thought we only had 4 quizzes.
No, we have 6, my friend.
Huh. Okay.
Right?
Yes,
Life,
sir.
life doesn't stop. Keep going, Arnab, right? Okay.